Welcome everyone. In today's class, we are going to discuss about C2 RTL equivalence checking for high level synthesis. So, as you have already know that this high level synthesis converts C code into equivalent RTL code, uh, and it goes through various sub processes like pre-processing, scheduling, allocation, binding, data path and control generation phase. Right. And there are two ways we can verify this process. One is simulation based verification and one is formal method based verification. And so, for formal method based verification, we already discussed in last class that this translation validation is something is very popularly used for high level synthesis. And in translation validation, we basically take one input program, we run through high level synthesis, we get a RTL, and then we check the equivalence between them, right. And inherently this equivalence problem is undecidable. So, we cannot have a complete method. So, if we can say yes, no all cases, yes for equivalence, no for non equivalence, but the method usually sounds. So, it means whenever it say yes, that means it is equivalent, and it may not able to detect whether it is equivalent or not, right. So, it will say may not. Okay. This we have already discussed. And also we have argued in the last class that this because this C and RTL, there are a lot of semantic gap, they are completely different execution pattern. So, having a direct C2 RTL equivalence checking is very difficult task, right. And as a result, most of the common research targets phase wise verification of high level synthesis, right. So, in the sense that you verify scheduling phase, you verify allocation and binding phase, you verify the data path and control generation phase, right. So, that we have already discussed, and in the last class we have seen the basic equivalence checking method, which is basically model this the input output of one phase as FSMD, finite state machine unit data path, and then we defined a equivalence of FSMDs, and then we have seen how we can apply adapt that equivalence method to verify the phases, right. So, that we have already discussed. Now, the point here is that this once you try to do a phase wise verification, which actually good, it basically verify all the difficulties of every phases, and you can actually point out the bug that actually occur in which phase, right. The bug might occur in scheduling phase, it might occur in allocation phase or so on, right. So, it can pinpoint that. But the disadvantage of the whole process is that you need the intermediate information, right. So, you need the scheduling output, right. So, whatever the scheduling output, you need to get that from the tool. You need the all information after allocation and binding, right. So, which may not be always available, specifically for commercial tool, this kind of information in detail may not be available. So, in such case verifying this phase wise is difficult, right. On the other hand, C and RTL, which is the input and output of the program, which is always available. So, having a end to end equivalence checking for high level synthesis, where you have only have the C code and you have the RTL, there is no intermediate information available with you, is something very important and is will be useful. Okay. So, that is something we are going to discuss, and we have already discussed that this particular it is a very difficult problem, the checking equivalence between C and RTL. It is a very difficult problem because of their semantic pattern, right. So, basically the way C executes, the way this RTL executes is completely different. Having this direct equivalence is a difficult process. But why? So, in this particular class we are going to discuss if we want to do that, what will be a possible way, right, and what are the limitations of that method and how we can do that, how can improve the efficiency of the whole process, right. So, let us discuss about that. So, the problem statement for today's class is that you have given a C code, you have given a RTL which is generated by the high level synthesis tool, any high level synthesis tool. From that input C code, and I want to check whether the C and RTL equivalent or not, right. So, that is the problem statement we want to do. And obviously, as I try to argue multiple times that this the way this C executes, the way RTL executes is completely different. So, having a equivalent checking method, basically the way I just defined, like if FSM device equivalence checking cannot be directly applied, right, because you cannot have a model of model of that Verilog versus the model of C, you cannot compare, right, their execution pattern is different. So, what is the way out? So, fortunately in the last class we have discussed about a converter, right, RTL to C converter, right. So, that we have already discussed. I hope you remember that. So, specifically the RTL that is generated by the high level synthesis tool is have a very specific structure that I have talked about, that it has a data path and a controller, and just analyzing the data path for each controller signal, each in state controller assignments, we can extract the operation that is happening in the data path, and this way that controller FSM convert into an FSMD, and our program model is FSMD, right. So, we have already modeled our input C behavior as FSMD only, right. And now I am talking about that this I can convert that FSM controller FSM into an FSMD. So, now these two is kind of comparable, right. So, that is something actually this RTL to C conversion actually gives an opportunity to do a end-to-end equivalence checking, which is something does not exist so far. If you look into literature at the current moment, there is no such open tools available, there is no commercial solution exists. So, there is no such offering, right, from industry or academia. So, but the point that I want to argue here is that this C to RTL conversion actually keeps open the door, right. So, you have C code, you have an FSMD which we represent by C code, but it is basically an FSMD. So, now we have two FSMD whose execution pattern is exactly same, the semantics are exactly same. So, I can now compare, right. So, the argument that I try to make, to do a C to RTL equivalence checking, you need some sort of similar representation, right. So, similar representation that I emphasize, otherwise you cannot compare apple with mango, right. So, they are two different things. So, similarly this we need to differ same representation, and fortunately because of this RTL to C conversion I have a similar representation now. So, this RTL to C conversion is helpful here, and that convert this C that RTL to FSMD, right, and I have the input C which we can represent as an FSMD, already we have discussed in the last class. So, now I can check, right, equivalence. So, that is the way I am going to do. Okay. Okay. So, this RTL-C conversion I have already discussed in the last class, that you have this controller FSM. Just to recap this, you have the data path. What I am going to do, in each state whatever the control assignment, I will analyze the circuit for this, and I will identify because of this control signal values these operations are happening, right. So, I will replace this by this. I am going to do this for all states. I am going to do this to all state, and once I do this, this is nothing but my FSMD, and this particular behavior has no clock, no reset, no memory, nothing. This is simple high level C code, right. So, that is what we have already discussed. So, this we can represent as a C code as well. So, this actually help us. Okay. So, the approach that we are going to take is that we convert this RTL into a FSMD by this RTL to C conversion method that we have already discussed, and now we have two behavior which is comparable. Now, I am going to check what could be the equivalence checking method here, what are the problems here. Although we have two FSMD, is it the same problem that we have solved for scheduling verification, allocation binding verification and so on, or it is something different, right. So, let us try to understand that. So, let us try to understand how this C and RTL-C, which is RTL-C is something the C that is extracted from RTL. Okay. So, let us try to understand that, and for that I actually I will see you some a real example that our tool actually generate from a benchmark. Okay. So, let me just show you that. Say I have this GitHub is publicly available, you can go into this FastSim. If you just search FastSim, you will get this GitHub. So, let us take a very simple example. Okay. So, this is a Waka example which has this is a behavior, right. This is my input C code. Okay. So, you can see here there are a lot of operations happening if else, and it has these are the inputs, right. So, there are 32 I mean so in 1 to in 32 there are certain inputs and there are 3 outputs. Okay. Now, if I run this particular code using Vivado HLS tool, I will get this RTL. Okay. You can see here fortunately the inputs are same, right. So, in 1 to in 32 the same inputs. it has all the same outputs, out 13, out 30 and out 31, right. Only thing it has some valid signal, which is basically say which time that particular out become valid, right. So, that something is there. So, I can conclude here that the input output specifications are exactly the same. So, here you can see the input variables are T1, T2, T3, these are the temporary variables that are used in this program, right. What about here? It has, you have to check the registers, right. So, you can see here there are so many registers, right, and so OR is basically intermediate signal, we do not have to bother about that, but if you see here the register some reg 361, some T61, you can see here there are many registers. So, one we can see that this very internal variables are different, input output are same for both Verilog and RTL, but the intermediate variables are different because here intermediate variables are the temporary variables of the program and here it is basically the registers, right. And why I am talking about register, because if you remember the rewriting method, we actually rewrite everything in terms of registers, right. So, finally, in the FSMD this OR will not exist, everything will be in terms of registers. Okay. So, now you see here this is I will talk about that. So, this is the FSM, controller FSM, right. You can see here that in state 1 if such condition hold, then I will go to this state, otherwise I will go to this state and so on. In this state I am going to do this. This is my controller FSM, the way I just explained, right. And these are the operations that are actually enabled in state wise. For example, if you see in the state 6, I am going to do this signal equal to 1, right. So, similarly, in this particular state 3, I am going to do these operations. Here this is basically a register transfer operation. So, now from this I will keep doing rewriting and there are this assignment statement which is are always happening, always true, right. So, I am going to, so for example, if you search this temp 294 P2. So, let us go to here, you can see here 294 P2. So, it is getting replaced by this, right. Then I have to take this and you have to take, I will try find operation which is basically will replace this, right. So, this way it will be rewriting operation is happening. So, this is the RTL, it is actually generated where this assign statement are the OR assignment which is always true, and these are the register transfer operations initiation happening state wise, right. So, from this behavior we are able to generate a C code, right. So, this is my generated C code, let me look into that. So, in this code, so as I mentioned that I am going to define every variable as a unsigned long int. So, these are the variables and you can see here the inputs are basically the same inputs, and you can see here so many variables has to define, right, and I just initialize them to 0, right. So, these are the all variables that is there in the Verilog. So, we have defined it and this is the behavior in state 1. I just assign that old to new things that I have already discussed, that what data inconsistency, and these are the operation is happening in state 1, right. So, under this condition I am going to state 2, under this condition I am going to go to state 1 and so on. In the state 2 again old to new assignments, new to old assignments, and then these are the operation is happening, right. So, then this is state 3 and so on. So, what we have seen here, so this is my input program which is basically of 30 lines, right. Here let us see the code, it is basically 380 lines. So, you can understand this is something completely different structure, the variables are different, operations are different, control structures are different. So, let me, so this is, so we have to check equivalence between this code and this code, that is the problem statement for us, and this is a very simple code. I open the smallest test case available with us. Okay. So, let us now move to the presentation. So, what we understood from a practical example, that once we have the C and RTL-C, we have the inputs out, outputs are the same, right, both has the same input output and they are the name is also same. So, that correlation is available with us. Control structure are different, they get changed due to scheduling, and the internal variables are completely different. So, for the C program the internal variables are the variables, and for this is registers, right. So, that is something is the given thing to us. Now, in the, if you just remember that for this that path based equivalence checking method that we have already discussed in the previous class, that we have talked about that this the basic equivalence when we can say two FSMDs are equivalent, that when you say for every trace or every computation of one behavior, there is equivalent computations, right. That means you give a input, you get a trace, one execution trace, and you find the equivalent trace in other behavior, and you do for all possible traces, right. So, this is n square kind of comparison, and we argued that because the loop, dynamic loop bound, when the loop bound is not static, it is input dependent, you might have very large number of this traces. So, that equivalence checking is a difficult problem, right, and because of that we actually insert cut points, right. We break the problem into smaller problems by introducing cut points in the behavior, and then we identify the path covers. The path covers is path between cut points, not the complete trace, and then we come up with an equivalence checking method which actually does not identify the trace level equivalence, rather path level equivalence, that for every path of this path cover we try to find a equivalent path in the other FSMEs. And since this path cover is a finite representation, so this equivalence checking problem becomes scalable, right, and it has the advantage that it can actually handle loops of dynamic bound, right. Now, let us try to see here if I try to do the similar approach and what is the problem, right. So, say suppose I take a simple example, let us say. So, suppose I have a path here. So, this is my say path 1 where say A equal to, so there are two inputs in 1 plus 5 and B equal to into minus 6, right, and this is my path 2. Here I am doing say out equal to A plus B and out 1 and out 2 equal to say A plus 10, right, and say this I decide a cut point, right, and this is a cut point say. So, these are the say cut points. So, there are two paths, and according to our previous definition I want to check the equivalence of this path, right. So, I will take this path, and now let us consider the corresponding RTLC behavior. So, this becomes say R1 which is in 1 plus 5, this become R2 which is into minus 6, and here this is out 1 equal to R1 plus R2 and then out 2 equal to R1 plus 10, right. This is my RTLC and this is my C. So, now if you try to compare this path with this path, so what will be the expressions of out 1? Out 1 will be A plus B, right, and out 2 will be A plus 10, right. This is the data transformation, and so there is no condition, and here what will be the case? It will be R1 plus R2 and A plus 10, sorry, this is R1 plus 10, right. This is my out 1 and this is my out 2. Now, problem is that once you try to find this path equivalent to this path, you have to compare this expression, right. You have to say the data transformations are equivalent, that means these expressions and these expressions are equivalent, these expressions and these expressions are equivalent. But here I cannot compare because they are using the intermediate variables A and B, here it is R1 R2, and I have no information whether A is R1 or B is R2 or not, right. So, I cannot just compare. So, that is a big problem, right. So, the problem is that this cut point based method won't work for this, because when you take a intermediate path, my data transformation or the expressions will be in terms of the intermediate variables, and the intermediate variables are completely different, right. So, I cannot just compare these two paths. So, that won't work. But now let us take the complete trace. So, this is the trace, right. So, this is a tau 1 and this is the trace tau 2. Now, let us try to explain again this try to rewrite out 1 in terms of inputs, right. So, down the rewriting will happen. Now, my out 1 will become A is in 1 plus 5 and B is into minus 5. So, it will become in 1 plus into minus 1, right, minus 1. This is my out 1 and this is in 1 plus 15, right, and here again it will become in 1 plus into minus 1 and this is in 1 plus 15. Because, so once you take a trace, I can actually represent my output in terms of the input and constant, right. So, now I can say these expressions are same, these expressions and this expression are same. So, I will say tau 1 equivalent to tau 2. So, the point that I try to make it here, that for this problem when we have the C and RTLC, since my intermediate variables are completely different, so I cannot just compare by intermediate paths, because their expression or representation will be in terms of the intermediate variable and there is no relation available with us. On the other hand, when you take a trace, trace is something the complete path from the input to output, from the start node to end node, right. So, for trace I can represent my output in terms of inputs only, because the intermediate variables are not defined, they are always get defined and used. So, they will be replaced by the inputs, right. So, finally, this output expressions will be in terms of the inputs and then I can compare, right. So, what the important point, that is very important, that whatever the path based approach that we have talked about for phase wise verification, we cannot apply here because of the intermediate variables, their correlation is not available, right. So, we cannot just do that, we have to do that trace level equivalence, right. So, we have seen that to compare two FSMDs, we can say that for every trace there is equivalent trace and vice versa, right. So, that is something we have to do here, there is no alternative until we have this correlation is given. Somebody, if you give that this variable R1 is nothing but A and R2 is nothing but, if this information is available with us, I can replace this by A, I can replace by this B, I can replace by this, and then I can say this expression is equal to this, this expression is equal to this, right. So, if this relation is available with us, we can actually go for that scalable cut point based equivalence checking or path based equivalence checking. Whereas, in this particular problem, that is, since this I assume that there is no intermediate information is available, this correlation is not available, I have to go for trace level equivalence. Okay. So, for that obviously we have to assume that the loop bounds are static, because if the loop bound is dynamic, so then I do not know how many traces are there. So, this particular if this bound is not given and if I say this is an integer, so I have to run for 2 to the power 32 iterations of the loop, right, or if it is a long int, it will be 2 to the power 64 iterations of the long int. So, those many number of traces will be there. So, we cannot assume that. So, we will assume that the loop bounds are static and it is a very strict bound, that your loops cannot have a dynamic bound. It will be always say I to 10 or I to 100, I to 10,000, but it is not I to n, n is an input. Okay. So, that must be there, otherwise the number of trace we cannot enumerate, right, that is the problem. So, now I try to argue. So, this is the first difficulty comes for making this C to RTL equivalence checking. And now I try to argue whether this static loop bound is very restrictive for high level synthesis, because we are try to do it for not for general programs, right. We are not solving the general program equivalence, rather we are try to solve the equivalence for high level synthesis. So, let us try to understand whether this is a too restrictive bound for high level synthesis or not. My argument is no. Why? If you remember, in high level synthesis we do not support dynamic memory access, right, dynamic memory allocation we do not access. So, the malloc, calloc, those one thing is not allocated. So, the array is basically a fixed bound, right. So, any array you cannot have, you can just malloc during the program execution, because that dynamic memory allocation does not supported by high level synthesis, right. So, it means that the arrays are of static bound or fixed size, right. Now, usually in the for loop what we do, and this for loops usually we manipulate arrays most of the time, right. And if the array is of fixed size, what is the point of keeping the loop bound dynamic, right. So, it will also be static. So, in general my argument is that in the context of high level synthesis, the static loop bound is kind of a very it is not too restrictive assumption, rather it is kind of very common, right. You do not find any for loops in high level synthesis context, where most of the time this high level synthesis context you will not find, very rarely test cases where for loop have dynamic bound, right. So, most of the cases it will be have a static bound, and hence this is not too restrictive bound. There may be some scenarios where your for loop can be of dynamic bound, but that is very rare scenarios. Okay. So, although this end to end equivalence checking is a trace level equivalence and path levels method cannot be applied, but we found that this which inherently tell us that you cannot have a static loop dynamic loop bound, but we argued here that that is not a too restrictive assumption. Okay. Let us now move on. So, program model, again we are going to use the FSMD. So, that we have already discussed. So, I am not going into detail of that is already discussed in the last class, and in FSMD we have paths, the similar definition that I have taken in the last class, and for every path we have a condition of execution and data transformation, which basically represent the final values of the every variable in terms of the symbolic expressions, right, in terms of the inputs or variables, right, and condition of execution is something, the condition that has to be satisfied by the path. So, I can actually have similarly I have computation and trace. Trace is basically a path which start from the start node and end in the end node. It is basically one execution of the program, right. And similarly, for this trace or computation, we can define the condition of execution and data transformation of the path. So, for this once you take that trace, we do not have to check the intermediate variables expression, we have to just check the expression of the output. So, the data transformation is basically the output expressions. Right. So, that is the difference from the earlier cases. So, basically we say that this because if you want to take a trace like this, right. So, suppose this trace you take. So, here finally your output will be in terms of the inputs, right. So, I do not have to take the intermediate value of say S, A, B, those things I do not need, because those are already intermediate variables. I have to just check once you have a trace whether the outputs are different equivalent or not. What is the intermediate variable, I do not care, alright. So, for this data transformations, it is not the expression for all variables, rather only for the outputs. Okay. And most importantly, in this context, as I already argued that once you take a trace, I can represent this condition of execution and this output expressions of any trace over the inputs and constant. So, the intermediate variable like A, B, S, those do not come to picture, because that I have already given an example here, right. So, I have already argued here, once you take a trace from the start node to end node, my output expression will be in terms of inputs, okay. That we have already understood. So, that something gives us the opportunity to compare the C and RTLC, otherwise we can't compare at all, right. So, that is the only correlation available, and we can actually utilize that and we can compare, okay. So, so that we understood that for every trace we will get a condition of execution and output expressions for every output, and those will be in terms of the input variables and constant, and we will say two traces are equivalent when their condition equivalent and outputs are equivalent. So, you take two traces, you say their conditions are equivalent and the output. So, if there are two output 1 is equivalent for both traces, output 2 is also equivalent for both traces, and this is a symbolic expression, there is no value, right. Then we will say two traces are equivalent. And the equivalence of FSMD is already discussed that for every trace there is equivalent trace in other behavior and vice versa. So, we have to make sure that for every trace there is equivalent trace there, and for every trace here there is equivalent trace there. Okay. So, that is how I am going to prove the equivalence. Okay. And as I argued that we have to go for this method, right. So, basically you have to check for all C0 of M0, there exists C1 in M1 such that C0 equivalent to C1, right. So, M0 contained in M1 implies this, right, and similarly M1 contains in M0 implies for all C1 belongs to M1, there exists a C0 in M0 such that C0 equivalent to C1. So, you have to check these two, then I can say M1 equivalent to M2, two programs, right, FSMD M1 and M2. So, basically what this particular, and we cannot go for this cut point based method already discussed. So, what we understand from here that we have to take a trace and I have to identify a corresponding trace, and if there are number of traces basically n. So, you have to take a trace and compare n, and you have to check for all n, right, you have to compare with all n to find out which is equivalent, right. So, that means order of n, and now if you have to do it for all traces here. So, the complexity will be order of n square of this. This is only the number of comparisons, and for every two trace the formula that I have to check, that also involves some computations, this into the complexity of formula equivalence, right, the way you want to compare the formulas. Okay. So, So, this is something the method that we are going to do, but what we try to say that, so this is inevitable for our problem. So, can we do some kind of technique, or you can apply certain kind of techniques which will improve the efficiency of the whole process. Okay. So, can I do these things in order of n, right, that is something interesting. So, we try to come up with certain techniques which is basically tell us to improve the efficiency of this C to RTL equivalence checking. Okay. So, this is the overall flow. So, this is that RTL to C conversions. The basic idea of here that we will identify. So, let us go into the method first. So, basically what I am going to do, I have to identify all the traces. So, I am going to find out all the traces in both the behavior. This is my input C code, this is the RTL, and then there is interesting things I am going to do is the merge compatible trace here, right. So, whatever the traces there, I will try to find out the compatible trace and I will try to merge them into one. So, it will reduce the size. Same thing I am going to do it here, right. So, they are not, I am not checking anything beyond this. Then the process is that you select a trace tau 0 here and you find a trace tau 1 here, right. So, these things I am going to use a method called data dependent method, right. So, that is very interesting. So, using that, from n square comparison I can reduce into order of n comparison. So, that is a data dependent checking. So, that I am going to talk about that. Once I found the corresponding trace, I have to check the equivalence, that this equivalence checking will be done by SMT tool, right. I will explain that also. And if I found they are actually equivalent, then I will go for the next trace, otherwise I will say they are not equivalent, they may not be equivalent. This is the overall process. The two interesting thing that we are doing here is these two, that merge compatible trace and this data driven finding corresponding trace using data driven approach. So, I am going to talk about the steps of the overall process. Okay. So, first thing is that you identify all traces in one behavior, right. So, given a behavior, we have to identify the trace, and for trace we have to identify the condition of execution and the output expressions. So, that we have to do it, right. And for that we have used a tool called CLI, which is a symbolic execution tool, and if you give a C program, you actually identify all the trace and their condition of execution and data transformation in symbolically, right. So, this is the link for the tool, you can actually try that. Let us take an example here. So, suppose this is my input behavior, and because of this conditional scheduling, for this the representation is this, and this is the final RTLC, right, say, and this is my C. I am not going to explain here how it is happening. So, one thing you can understand here that there are two traces here. I take a very small example to explain, and here there are 3 traces, right. So, there are 2 traces here and there are 3 traces here. So, you can understand here that the number of traces may not be same in both the behaviors, and because of the conditional optimizations. So, if you just compare for this path, you may not find a equivalent path there, right, equivalent trace there. So, that is a problem, right. So, but this is the first step. Given the behavior, I will identify the number of traces in C and I will identify the number of traces in RTLC. Okay. This is my step 1. Next is very interesting, is a merge compatible trace. What I am going to do? We identify that the number of traces in both the behavior may not be the same, okay, but there may be some trace within the behavior. So, I am not taking 2 behavior now, I am going to take a single behavior. Say let us say I took this behavior now, and I try to identify 2 trace. Say this is the trace 1, this is my trace 2. In these 2 traces, I try to identify if the data output expressions are same or not, right. So, let us say here the output is basically say R3, right. So, I can see here that this is also C into D, this is also C into D, right. So, that means the output of these 2 traces are actually equivalent, right. So, this is also C into D, this is also C into D. So, this is basically compatible trace. So, basically we will say these 2 traces are compatible within a particular program if their output expressions are same. Okay. In that case, I am going to merge this into one. So, how will do? So, whatever the condition of this path, say this is a condition is a tau C1, and this the tau condition will be tau C2. So, this will be my condition of the merge computation, right. So, I will just merge into one, and the computation, this condition of execution will become OR of these 2 conditions, and expression is same. So, the output expression will remain C into D, right. So, this is the first thing I am going to do, and we found that this is very important, otherwise the complexity of your equivalence checking will grow, and we found many cases this kind of compatible traces because of the conditional transformation. This kind of thing happen, and you can actually find out the compatible trace and merge them into one, right. So, this is the first step I am going to do, but we found several scenario where the number of traces even not become same for both the program after merging. For this case it will become same, there are two trace here, trace 1, trace 2, here this will be trace 1 and this union will be trace 2. So, there are two traces. So, for this case the number of traces becomes same after merging compatible traces, but in general the number of traces may not become same even after this because of some complex transformation which stop us from merging this compatible trace. Okay. So, but this actually an useful tricks to reduce the complexity, because whatever I am saying I have to compare this trace versus trace, but the technique that I am going to propose here will reduce the complexity. So, here because 2 and 3 I cannot compare, so I merge this 2 trace into 1, now 2 into 2, so I can compare them easily, right. So, that will reduce the complexity of the equivalence checking. Next I am doing a very interesting thing is that find potential corresponding traces between two behaviors. So, what I have told you that you take a trace here and there are say n number of traces here, right, in this program 2, this is program 1, this is program 2. So, if you have to compare this with this, this with this, this with this, this with this and this. So, it is basically all n you have to compare, right, and I have argued that if since there are n number of traces here, it will be order of n square complexity, that I have already talked about, right. So, can I reduce this complexity to order of n? Yes. So, we can do that using a technique called data driven approach. So, idea is very simple. The idea is that you take a trace here, okay, and you identify a input for which this trace will execute. Okay. Now, you apply the same trace to this program, right. So, if you give the input to this program, what will happen? One of the trace will execute, right, not all of them, because if you give an input only one of the trace will execute. So, now suppose I took this trace, and I take a input which actually makes sure this trace will execute, and now I apply this trace this input to this program, and I found that this is the trace that is going to execute for this input. I will say these two traces are potentially equivalent, right. So, now I do not have to compare with all traces. So, I will just take this trace tau 1, this trace tau 2, and I will just check whether they are equivalent or not. If I found they are equivalent, then I will say ki yes, they are equivalent. If not, then I will say ki this program may not be equivalent. So, I am not comparing this with all n, rather with an input, with the help of input I identify directly the corresponding trace. Okay. And so, this n order of n checking is gone. So, the overall complexity will become now order of n, not n square, right. So, that is the basic idea of this, and we can again use the tool CLE to do this. So, CLE you can actually set some input and it will give you a trace, and then with this input you can actually identify the corresponding trace, right. So, we use the tool and that actually helps to reduce the complexity. Okay. This is the basic idea. So, once you have this potential trace, right. So, I have trace 1 here, I have trace 2, right. So, tau 1 and tau 2. The next problem is that you have to compare these two, right. So, these two traces whether they are equivalent or not, and this comparison we have two arithmetic expression we have to compare, right. This comparison how can I do? So, for that we use a tool SMT solver, and with the tool we use Z3. Okay. So, the idea here is that, and this SMT solver is basically just check the satisfiability of some formula, right. So, the equivalence problem of these two paths has to be modeled as a satisfiability formula for a solver, SMT solver. So, how we can formulate that? The formula is that, so for this tau 1 we have tau C1, sorry, this C tau 1 which is the condition of execution, C tau 1, and the condition of execution is C tau 2 here, and it has a O alpha, sorry, O tau 1, which is the output expression for this, and for this it is O tau 2, right. This is the things we have. Now, I have to model a satisfiability formula. So, there will be a formula which will be either satisfiable or unsatisfiable, right. And the way I have to model this equivalence problem of path into the satisfiability formula such that when the formula become unsat, I will say these two are equivalent. Okay. So, that is the idea. So, how do I going to model it? So, I will say that C tau 1 equivalent to C tau 2 and O tau 1 equivalent to O tau 2. So, if you just try to you just give this formula and you ask the tool, you just find a SAT, right, check SAT. What it will do? It will basically check this and it will try to find out an input for which it will this formula is true, right. So, now the problem here is that it just return one input value for which this formula say it is true. Okay. So, as a result you are not actually formally proving the equivalence, right. It just say ki for this input this formula is satisfiable or true, right. So, what I am going to do, I will take the negation of this formula, okay, and I will check the unsat, right. So, I will now check the set again. So, what will happen? I try to, so what does it mean? It means here that you find an input for which these two paths are not equivalent, right. If the tool find a input for which these two paths are not equivalent, then indeed it is basically they are not equivalent trace, right. But it's if it is return unsat, what does it mean? It means it does not find any input for which this path are not equivalent. What does it mean? It is basically equivalent, right. So, I basically take the negation of the satisfiability problem and ask the tool to identify a input for which these two paths are not equivalent. And since these two paths, if the paths are equivalent, you will not find any input for which they are actually different, right. So, it will return, so this formula is unsat and the unsat of the formula says these two trace are equivalent. So, this is how I am going to check the equivalence of two trace, okay, using the SFD solver. And I have seen that in some cases if the one to one correspondence cannot be shown, then we have to do one to many equivalence, right, and that is need order of n square, order square checking, but we will say we will only do it for very few traces for which one to one correspondence cannot be proven. Okay. So, that is what the idea of this. So, in worst case we have to do this, but this research will be done for very not for all n, right, it will be for some n1 number of things where n is very less than n. Okay. So, let us now explain the overall algorithm. So, as I said, so you identify the traces. So, you have given two programs C and RTLC, you model them as FSMD, you find the traces in both the programs and you also find the traces and then you merge the compatible traces also. So, you reduce the set. Okay. Then what I am doing is very interesting, this is this one to one correspondence, right. So, this is one to one checking and this is basically one to many. Okay. So, in the one to one what I am doing, I will just take a trace of this one program and for that I will take a test case and then I run the other program with this test case to get a corresponding trace, the potential corresponding trace. So, I am checking order of n square, you see this is order of n algorithm and this is order of n square algorithm. There are two for loops, right, here only one while loop. So, I identify a corresponding trace and this is the formula I am just checking, right. So, whether they are equivalent or not. If they are equivalent, so I will say I identify the equivalence. So, I will just remove these two traces because for them equivalence is already obtained, and if I found that condition is same, but the data transformation is different, the output is different, then I say they are not equivalent, because if the condition same, these two traces are basically must be equivalent, otherwise it is a problem, but I found that output expressions are different. So, I will say they may not be equivalent. Otherwise, what I will say, this trace tau 1 I cannot prove the equivalence. Okay. So, for this order of n square is needed, right. So, I will just keep that into this copy of T1, right. So, in the copy of T1 I am just removing all the traces for which equivalence is found, and the trace for which equivalence cannot be found in order of n time, I will keep them into copy T0 tau 0 this traces, right. So, this will go on for all traces, and for all cases where one to one equivalence can be proven, it will be done here, right. If it is not done here, the remaining traces will remain here, and for that you can see I am doing an order of n square checking, and what I am doing here I will just so basically what is going to happen. So, there is a trace and this is say the condition space, right, and there will be multiple trace here. So, this is the condition for one trace here, and there may be one trace which will which condition will be this space in the other program, there will be another trace for which the condition will be this part, and there will be another trace for which condition will be this part. So, these three trace, so this is say tau 1, tau 2 and this is tau 3, which will be union of these three will be equivalent to tau. So, tau is the complete condition. So, that is what is happening here. So, I will take a trace tau 0 and I will identify a trace tau 1, so that their condition is non null, that means there are some overlap. So, I will identify this part, okay, and then I will see if their output expressions are then equivalent, right. So, what I am going to see, I identify a trace in the other behavior whose condition is basically subset of this trace, and I will check if their output are equivalent or not. If they are equivalent, then I will say it is fine, if not, I will say they may not be equivalent, right. If they are equivalent, I will go for, I will identify the next one. So, I will now identify tau 2 and I will identify their subtrace are equivalent, and then I will again check their output expressions. If they are same, I will say they are equivalent, move on, and then I try to find out the next trace tau 3. So, this way this inner loop will identify for every trace tau 1, it will identify all the traces which is basically condition is subset of this condition of tau 1, and since this program is deterministic, the union of this C tau 1 union C tau 2 union C tau 3 will be equivalent to C tau, right, because this is a deterministic program. So, this way for every trace I will identify set of traces in other program which union of them will be equivalent to this trace. Okay. So, this you remember that again I am not doing for all traces, because most of the cases the equivalence will be found here, only very corner cases I have to do this. So, this is the overall idea, right. So, what we have done here is that this still this trace level equivalence has to be done, but we try to do several kind of tricks to reduce the complexity. Okay. So, let us explain some examples here. So, experimental results. So, these are the test cases we have taken, and you can see here these examples are moderate size, the number of variable is high, and this is the RTL code size, and this is the RTL-C. So, it is the number of line of code is much higher than the C code, and we have also seen that things in an example, right. Interesting things to be noticed here, that the number of registers. Okay. So, number of registers here, and this is the number of variables. Here you can see that it is always less than the number of variables, 32, 12, 43, 29, right. So, usually because this the register allocation happen, so most of the cases is basically the number of registers. So, try to optimize the number of registers, right. So, it says the number of registers is less than the number of variables. Some cases it is basically more, because this array map to registers, right. So, there are two cases, the matrix array and sum array, where this array is a single variable here which is mapped to register. So, that is why the number of register is more in this scenario, otherwise it is always the same. And this is the number of traces. You can see in many cases the number of traces are not equivalent, right. So, the number of traces are not equivalent, we can understand that. So, this is, so that is why this compatible trace is important, and the number of traces are not equivalent here also. So, then we do the merge compatible traces, and after that this is the number of trace in program 1, this is the program 2. You can see here after that most of the cases the number of traces become equivalent except one scenario. So, this tell us the usefulness of the merge equivalent traces. Many cases the number of traces are not same before merging compatible trace, but after that they become same, right. Most one important thing is that there are 128 of trace and there are 128 traces here, this 128 trace merge into and become 8 traces. So, merge compatible trace helps to reduce the number of traces also, because we found that there are numbers of traces where the outputs are equivalent, I can merge them. So, the complexity also reduce here. So, this is a very interesting and important step which actually make my problem or this equivalence checking problem scalable, right, or actually make it very helpful. Okay. So, then after that we check. So, you can understand that. So, out of this I think there are 7 or 8 test cases are there, 7 test cases the number of traces become equivalent, only one cases it is not equivalent. So, most of the cases in this scenario order of n will suffice, right, only this case I have to go for order of n square checking, because the number of tests not same. So, this is very helpful, right. So, most of the cases merge compatible trace reduce the problem into a such problem that that one to one corresponding checking can help, right, and we can identify that the number of time taking is very less, right. So, most of the case within seconds, right. So, only case where you have to go for n square the time is more 1000 seconds, right, but still the time is not so high, right. So, this because every cases we are actually using, we call the SMT solver, and that takes lot of time, because that actually check the formula, then it checks the unsat and sat. So, it also that this time involves that SMT time as well. So, we can understand that including the SMT time also, the time is also very reasonable. And then we identify many, we basically take this example, we introduce certain bugs in the RTLC and we check the non-equivalent, and most of the time we very quickly also prove the non-equivalence, right. So, it shows that if there is a bug, our tool can easily detect it, right, and if there is no bug, we can show the equivalence. Okay. So, that is all. So, just to summarize, in this discussion we propose an RTL 2C translation validation framework, right, for high level synthesis. So, we have a RTL and C, we try to propose an equivalence, and to make this particular equivalence checking framework, there are certain things is very innovative in our flow. First of the things is that this extraction of the RTL-C, unless we have the C behavior, we cannot just compare. So, this RTL to C conversion is very helpful and very interesting in this context. So, that only enable this whole problem, and also we propose this merging compatible traces, which is also help us to reduce the complexity in most of the time, and is used to make the number of traces is equivalent in or equivalent or same in both programs. So, that is also very useful. And then we also use a approach called data driven approach, which actually help us to identify the potential equivalent trace between two programs in order of n time instead of n squared search. So, that also improves the efficiency. And finally, the formally you have proved the equivalence of two trace formally using the solver SMT tool, right, Z3. So, this is the overall idea. Okay, thank you.